Welcome to this explainer. Today, we are strapping in and unpacking a truly high-stakes story that bridges the unimaginable scale of the cosmos directly to the literal flick of a light switch in your living room. We're blasting off to look at the fiery, volatile dynamics of our sun, and then we're going to trace that raw astronomical energy all the way down to the local power lines running right through your neighborhood. It's a thrilling story of cutting-edge space science, massive engineering, and a hidden vulnerability we walk past every single day. When most of us think of extreme weather, we picture howling winds, torrential rain, or blinding snow. It's loud, it's visible, and it's something you can physically feel. But there is a silent, completely invisible weather system raging right above our heads: space weather. So what actually happens when the sun unleashes a magnetic attack on our planet? Well, we aren't talking about getting a bad sunburn here. We are talking about a silent force capable of melting thousands of pounds of solid terrestrial metal inside the very transformers that power our civilization. Do you truly know the danger looming just beyond our atmosphere? Okay, let's dive into this. Here is our roadmap from the macro to the micro. 1. The invisible cosmic threat. 2. The 1989 grid collapse. 3. Modeling grid vulnerability. 4. The SMILE mission. And 5. Preparing for future storms.
Section 1. The invisible cosmic threat. To really get what's at stake here, we first have to zoom out, like way out. The sheer scale and immense power of the astronomical forces at play just outside the thin blue line of our atmosphere are absolutely staggering. Now, our planet has a phenomenal natural defense system, and it's called the Magnetosphere. See, Earth is constantly being bombarded by gentle streams and occasionally extremely stormy bursts of charged particles ejected straight from the sun. Luckily for us, the Magnetosphere Ox is this massive magnetic shield that stops the vast majority of these particles from ever reaching the surface. It is a brilliant, invisible bubble of protection. Quite frankly, if it weren't for the Magnetosphere, life as we know it simply could not survive on planet Earth. But sometimes that shield gets pushed to its absolute limit. So how does a space event actually become a problem on the ground? Well, let's walk through it step by step. Step 1, the sun violently ejects a massive burst of solar wind. Step 2, this stormy material travels across space and literally slams into Earth's magnetosphere. Step 3, this intense interaction injects charged particles deep into our upper atmosphere, forming massive swirling electrical currents around the poles, which we call ionospheric electrojets. And finally, step 4, these electrojets fluctuate so widely that they actually induce a geoelectric field in the surface of the Earth itself. This pushes what we call geomagnetically induced currents, or GIC, directly up into our ground-level electrical grids.
Section 2. The 1989 grid collapse. Now, if this all sounds like, abstract space physics, I need to bring you right back down to Earth. Because this invisible enemy has struck before, and the historical evidence of its power is both real and frankly terrifying. Look at the shocking speed of the Great Geomagnetic Storm of March 13, 1989. At exactly 0740 Universal Time, the massive Hydro-Quebec power grid in Canada completely collapsed, gone. Just a few hours later, at 1050 UT, the escalating storm caused widespread impacts across the United States power grid. And by 2120 UT, the US grid was experiencing extreme reactive power demand peaks. Essentially, the entire system was gasping for the electrical stability it desperately needed just to stay alive. The escalation was breathtakingly fast. And this brilliantly illustrates the sheer, devastating magnitude of the forces we are dealing with. During a major storm, those ionospheric electrojets flowing about 100 kilometers above the poles can carry a staggering 1 million amps of current. It's literally an ocean of electricity raging in the sky, completely invisible to the naked eye, but powerful enough to rip right through the magnetic field and violently shake the electrical infrastructure anchored in the dirt below.
Section 3. Modeling grid vulnerability.
So how do we fight an enemy we literally can't see? Well, we model it. We have to pivot from historical disasters to the deeply complex mathematical modeling that electrical engineers are doing right now to understand exactly where our grid is weak. Now, you might have heard about the 11-year solar cycle with its peaks of high sunspot activity, but here's the thing. Relying entirely on sunspot counts is a flawed metric for our safety. The data actually proves that massive, world-shaking geomagnetic storms can and do strike unexpectedly at any time during that cycle. In fact, some of the most dangerous historical storms have happened far away from the sunspot peak, which keeps our modern power infrastructure in a state of continuous, unpredictable vulnerability.
Now, what's really interesting about this slide is the profound irony of our own human progress. Over the last several decades, the United States high-voltage transmission network has grown tenfold. We've built this incredible, sprawling web to deliver power more efficiently to everyone. But in doing so, we have literally built a giant space weather antenna. Because these currents are induced over long geographic distances, a larger, more interconnected grid actually captures way more of the sun's destructive energy. And the engineering data gets even wilder when we look at the specific hardware. To make our grids more efficient, we've steadily moved to higher and higher voltage networks, from 345 kilovolts up to 500, all the way to 765 kilovolts. But those higher voltage classes drastically increase our geomagnetically induced current vulnerability. Under a high GIC impact, a 345 kilovolt transformer faces severe heating and failure. A 500 kV unit faces extreme reactive power loss. And the 765 kV giants, they become a critical threat that can trigger a total system collapse. Our very pursuit of efficiency has actually amplified our risk. Because the threat is just so massive, engineers use what are called mesoscale ground conductivity models. This is essentially mapping how different types of underground rock and soil conduct electricity. By doing this, scientists can accurately predict where the geoelectric fields will be strongest, revealing exactly which regions of the U.S. power grid will be hit the absolute hardest when the next solar storm washes over the continent. Section 4. The SMILE mission. But hey, we aren't just sitting around waiting in the dark. Space agencies around the world are stepping up, launching cutting-edge scientific tools to study the sun and protect our way of life. Enter the SMILE mission. Launched on May 19, 2026, the Solar Wind Magnetosphere Ionosphere Link Explorer, or SMILE for short, is a monumental leap forward in our space race to decode solar weather. For the very first time, this remarkable spacecraft is going to give humankind a complete, continuous look at exactly how our magnetosphere reacts to the violent material the sun throws our way. So, the crucial point is that this mission is absolutely packed with groundbreaking firsts. SMILE isn't just looking at fragments, it's capturing the very first X-ray images of Earth's magnetic shield in action. It's going to continuously observe the ultraviolet auroras for 45 hours straight. It represents a historic joint implementation by the European Space Agency and the Chinese Academy of Sciences. And it does all this from a sweeping 121,000-kilometer highly elliptical orbit. It completely moves us away from isolated, detail-oriented guesses and gives us a clear, global picture of our cosmic defenses. Section 5. Preparing for future storms. Armed with all this incredible new data from space and our deep Earth modeling on the ground, we have to connect the macro to the micro to see what the future actually holds for us. When we contrast that famous 1989 Quebec collapse with current predictive models, things get very serious. Engineers model what they call a 1-in-100-year extreme scenario, which is a terrifying magnetic disturbance fluctuating at 4,800 nanoteslas per minute. The 1989 storm was bad, for sure, but a direct hit from a 1-in-100-year extreme storm on today's expanded grid, that poses an exponential danger, with the potential to trigger catastrophic, cascading transformer failures across multiple regions simultaneously. Let's move to and see how this builds. This threat actually compounds when we look at how the ground itself reacts. If a massive 2,400 nanotesla per minute electrojet event hits, some regions, like the BCA2 geology, only see a 2.2 volts per kilometer field. But look at the SOS2 region. It absorbs a massive 15.6 volts per kilometer hit. Depending entirely on the dirt beneath your local substation, the invisible threat from space is magnified nearly 7 times over. And that brings us to the profound realization at the heart of all this research. As the official assessment explicitly states, the problem of power system impacts is compounded by growing vulnerability of this infrastructure to geomagnetic disturbances. It is a really heavy truth to grasp. Our incredible technological progress, our sprawling, highly efficient, interconnected, high-voltage networks is simultaneously our greatest structural weakness against the ancient forces of space weather, which leaves us staring up at the sky, asking the ultimate question. With everything we now know about the magnetosphere, the electrojets, the deep Earth conductivity, and the vulnerabilities inside those massive transformers down the street, is our modern grid truly ready for the next massive solar storm? Or are we just waiting for the lights to go out? Thank you so much for exploring this fascinating intersection of space and Earth with us today. I highly encourage you to look up how your own local power grid is preparing for the invisible cosmic weather above.